Okay, we're going to talk really briefly about the atom, just the structure of the atom. And as you might remember from grade school, an atom is composed of three particles: a proton, a neutron, and an electron. Now, the proton and the neutrons, the protons and the neutrons, they clump together and form what's called a nucleus at the center of an atom. Now, the protons have a charge of +1, plus, remember it's a positive charge. This is an electrical charge that we're talking about. And the neutrons are neutral. Neutron, neutral. That's pretty easy to remember. And then you might have seen an old classical model of electrons orbiting in a circular orbit around the nucleus. That's not exactly the way it happens. What really goes on is much more interesting and very counterintuitive. We might get to that in some other videos. But for right now, we're just going to say that the electrons basically encompass some kind of volume around the nucleus. And each electron has a charge of -1. And they're basically held there by the positive charge of the proton. So just like imagine two magnets. You have a north pole and a south pole. Well, if you put them together, they're going to attract each other, right? So you could kind of think of this as a north pole and this as a south pole. And it's not magnetism, it's electricity. So it's a little bit different, but you could imagine it like that. Now, let's talk about the masses of these particles. Protons and neutrons are pretty close together. The neutron weighs just a slight bit more, but at three significant figures, they weigh 1.67 times 10 to the negative 27th kilograms. And an electron only weighs 9.11 times 10 to the negative 31st kilograms. Now, to put this into perspective, if let's say an electron weighed 170 pounds, about an average grown person, right? 170 pounds, then one proton would weigh 300,000 pounds. So you can imagine that you could have like 20 or 30 electrons, and that's not even going to make a dent in the weight of one proton. So when we consider the mass of an atom altogether, you could completely forget about the electrons, and it's not going to make any bit of difference towards the entire weight of the atom. So, and to give you another sense of scale, if the nucleus here were the size of a golf ball, then the volume that the electrons would take up, the radius of that volume would be 1 kilometer long. Or you could also think about it as if this were the size of a period at the end of a sentence, then the radius would be 50 meters long. So again, it's quite different from what this picture would lead you to believe. So now let's talk about atomic mass and atomic number. So the atomic number is the same as the number of protons in an element or in an atom. Okay? So right here we have strontium. You could look that up on the periodic table, and it's number 38. And that corresponds to the atomic number. So for instance, sodium is 11, I think, and hydrogen is 1, helium is 2, and that number corresponds to how many protons there are in the atom. And it actually turns out that the number of protons defines the identity of the atom. So if you have an element with 38 protons, no matter what, no matter how many neutrons or how many electrons you have, that is going to be strontium, no matter what. If you have an atom with 2 protons, like we have here, well, all right, let's think about that. 1, 2, that's 2 protons. So let's look, therefore the atomic number is 2. And if you look on the periodic table, the second element, number 2, is helium. So this right here would be helium, okay? And for the atomic number, we would put 2. Now this, the mass number. Like I said, the number of electrons won't affect the mass at all because it's so tiny. So if we add up the total mass, that's really only dependent on the proton and the neutron. So let's just look at this example that I've drawn right here. Well, we're going to define what's called the atomic mass unit, or AMU. It's the atomic mass unit, and that is about equivalent to the weight of one proton. And since a proton and a neutron, there's an actual number for it. I'm not going to bore you with that. But since protons and neutrons are pretty much the same, they're very, very close, then we're going to say that they each weigh 1 AMU. So we write the mass number, as the total number of particles in the nucleus. So the total number of protons and neutrons. So if I'm just going to look at this and count it up, we have 1, 2, 3, 4. Okay, so that's going to be 4. It has an atomic mass number of 4. In this case, with strontium, we have an atomic number of 38, which means automatically, you don't even have to think about it. If the atomic number is 38, then that means it has 38 protons. So how many neutrons are in this strontium atom? Well, if this is the total number of all the protons and all the neutrons, well, then you just take 88, that's the total number, and you minus the number of protons, which is 38, and you get 50, so that must be the number of neutrons. So now this brings up the next topic, I guess, which is an isotope. An isotope is an atom with a different, or two isotopes are two atoms that have different numbers of neutrons. Because an atom is defined by how many protons it has. You could have the strontium-38. It is strontium because it has 38 protons. But you could have strontium, let's say 87. And that would mean that instead of having 50 neutrons like this one had, then you'd only have 49. The interesting thing here is that you could change the number of neutrons in an atom, and as long as you have the same number of protons, the atom remains the same. Now, how could that be? I mean, you're losing mass, the mass isn't going to be the same, but if you think about it, what was the thing about neutrons? They were neutral. They had no charge. So, if the only thing that has a charge in the nucleus is a proton, and it has a positive charge, then the amount of positive charge that you have in an atom, right? You have this proton here, this proton here, this proton here, and let's say we don't have any neutrons. Well, you still have a total of 3, right? The positive charge of plus 3. So it would like to attract 3 electrons, right? So you'd have a total of 3 electrons in the area around it. And now let's think about the area, the actual volume of the atom itself. Well, that was dependent really on only the electrons, right? Because the electrons, you know, if this were the size of a golf ball, they'd be a kilometer away from here. So, since this guy is capable of attracting that many electrons, then really the identity of the atom, if you were to throw something up against the atom, then it depends only on the electrons that are around it. And having a number of protons determines all of that. And it's a little bit more complicated than just having, you know, three electrons, but we'll get into that. Now, so to recap, basically, we know that these weigh a lot more than this, and therefore the mass number is only dependent on protons and neutrons. The electrons don't even come into play when we talk about mass. The atomic number, which is the number of protons, identifies the element, and the total mass number is the number of protons and neutrons together.